many I got over there? I got 1, 2, 3, 4 over there. Okay, we got folks over there. We got folks over here. The neighbor's pasture exploded with baby cows on Saturday morning. Friday night, there was like 1 baby cow out in the pasture. By Saturday morning, there were like 50 baby cows out in the pasture.
Sounds like a productive day.
Yeah, it was just, the weather was just kind of entertaining, I guess. So, on Friday, we finished up a little bit about flux. We talked about electric fields, and we've talked about forces. So far what we've done is we've started with force, got to electric field, and now we're going to go into, this is going to get us from electric field into a device. And I even showed you the device that we're going to start with, and we're going to start with a capacitor. But to get there, we want to talk a little bit about potential energy, because you don't go into the lab and you don't go into the various places and you measure the electric field. That's not something we measure. We typically will measure something else, and we typically measure what's known as potential. We look at electric potential. And so how do we get to electric potential? Well, remember back in Physics 1, we talked about potential energy, we talked about kinetic energy, and we talked about a variety of different things. So if I look at remember the slide, because I always use my slide as my example, that the total energy in the system is going to equal the potential plus the kinetic energy. And the work gets us back towards that potential energy. So if I had potential energy due to gravity, that's mass times gravity times the height, because I have potential due to position. Well, when we look at the electric field, we saw on Friday that if I put a test charge, I put my little electron in my electric field, it's not going to stay put. It's actually going to end up moving. And if it's a positive, or if it's a positive test charge, it's going to move away from the positive side of the electric field towards the negative side. If it's a negative one, it's going to move towards the positive side. So we look at that work that we have. So let's kind of look at the diagram here that you've actually seen in your book. And I'm going to actually write out a little bit different. I'll switch over to the document camera here. But I have my uniform electric field. I've got 2 plates. I've got a uniform electric field. And if I put my test charge in there, my test charge right here is going to experience a force. Okay, it's going to experience a force, and that force is the charge times the electric field, and it's going to want to move. But if I could actually hold it there, it's just like that picture where they showed between the 2 electrodes, they were holding that atom between those 2 electrodes that I showed on Friday. I'm actually holding it there, and when I finally release it, it's going to actually move. I'm going to end up with potential energy associated with where my little test charge is. I'm going to have that energy of position. So if I go back to the work is the force times the distance. So I've got my distance that this little electron is going to move. That's my change in x. But my force is my charge times my electric field times the distance. And recall, this is a scalar product. I no longer have to worry about what direction that vector's in, because it's just like working with potential energy. I got rid of that work with the potential energy by doing what we call the scalar product. So I can go in there and I can look at the work, and we can use that work energy theorem that we had before. And the work energy theorem was that work was equal to the change in kinetic energy, or the work was equal to the change in potential energy. And what we're going to do is we're going to talk about that change in potential energy in terms of electricity as the difference between the potential at this point and the potential at that point. So there's my change in potential energy is related to this, and that's the change in my potential energy divided by my charge. So I'm going to look at that particular spot, and I'm going to have that change, and that's going to relate back to that change in position, and it goes back to my work energy theorem. So I'm going to do a couple of things here. So if I've got my charge here, switch to the document camera, make sure everything switches. So we can actually do a couple problems, and it's like how much work does the electric charge do moving a minus 6.0 microcoulomb from ground to a point whose potential is 80 volts. So one of the reasons I'm going to do this problem is actually do the unit analysis associated with 80 volts. And we're actually going to do the work and do the calculation associated with work. So my work, remember my work is going to equal my negative change in potential energy, and that's going to equal my work. And we said that the change in potential energy is QE. I want to make sure I'm writing this. So I got my force QED. That's my change in potential. That's my change in my work. And my electric potential we've defined as the change in my potential energy divided by the charge. That's where my electric potential is. And that is going to also equal the work divided by my charge. I've got something funky. I don't think that goes there. And this ends up being minus Q times my potential. And then I end up getting my work is equal to my minus Q times my potential. And I get my minus 6.0 times 10 to the minus 6 coulombs times my potential, which is 80 volts. And that gives me volts. When I do my volts is going to also equal joule per coulomb. So when I do this, I get my minus 6 times 10 to the minus 6 coulombs times joule coulombs, and that's 80. And that gives me 4 point, and there's a minus, it's a minus, that gives me 4.8 times 10 to the 4th joules, because the coulombs cancel out. You also will get in your text and a variety of things. A lot of times we'll do this, 1.602 times 10 to the minus 19 joules is equal to 1 electron volt. So that's a conversion that we'll use a lot. And my electron volt is a unit of energy, and I have to kind of keep track of that unit of energy. And then just to also do that, if I do that, I did that, no, that was right. This was right, guys. I did that. My notes are just screwy today. I'm just glad I'm not having as bad a day as a lot of other people, because I got several emails this morning that things are not going well with all this yucky weather. So my electric field is going to equal my change in potential divided by my distance, and that's going to give me volts per meter. And I want to show you that this is also equal to Newton coulombs. My volt is equal to a joule coulomb, so a volt per meter is equal to a joule meter coulomb. And then I have, that's right, joule meter coulomb, and a joule is a Newton meter. Meters cancel out, and I end up with Newton coulombs. So as I told you, even though I harp on it in Physics 1, we harp and harp and harp about using unit analysis, my unit analysis is going to start to get really funky, because We're going to start talking about volts. We're going to start talking about ohms, and that's an ohm, and that's a unit of resistance. We're also going to start talking about amps, and that's a unit of current. And so it starts getting really confusing to do your unit analysis as you work through things, because it's hard to remember exactly what my volt is, what my ohm is, and what my amps are, and it's just a little difficult to try and go through that unit analysis, but we can still do it if we go back and look at it and kind of keep track of where we're at. So we will end up getting that lovely unit analysis and going back to the different voltages. But the nice thing, why we want to get there, is I can measure voltages. I can actually measure voltages. There we go. I can actually get that. It's something I can measure. I can go to the store and buy electric potential. In fact, all of you, I am pretty darn sure, has a source of electric potential on your person right now. That lovely battery inside your phone or your computer or whatever, that's a source of electric potential. So I can actually use it, and I can actually measure it, and I can actually keep track of it. So electric potential for a point charge, when we actually look at our point charge and we go in there, that my electric potential, and I just showed you that my electric field is my voltage divided by the distance, and I can get in there, and if I do that with that electric field, I'm going to end up with voltage is equal to Coulomb's law times the charge divided by the radius, or how far away I am from the source of the charge distribution. So how far away I'm at that charge distribution, I'm going as 1 over r. So I'm actually going to go as 1 over r instead of 1 over r squared. So if I actually graphed this out and looked at the graph, my electric field goes away as 1 over r squared. My electric potential goes away as 1 over r. So my electric potential is going to go back, and remember, I'm going to look at this as that's the potential energy as if I put that point charge in a position away from a charge distribution. So it does depend on the distance. So just like how far away I hold the ball away from the surface of the earth, I'm going to end up with that potential, and I'm going to calculate it doing KQ over R. I still have some interesting things that work for us. My electric potential of multiple point charges, I still use the superposition principle. I still can do those adding there. The total electric point potential at some point P is due to several point charges is the algebraic sum of those potentials. And I can do the algebraic sum because now I don't have to deal with because everything's a scalar quantity, I don't have to deal with that vector direction. So it's a lot easier to handle and manipulate than trying to deal with my electric field. Because remember, in my electric field, I have to take care of that vector notation that I have to watch out there. Same with my force. My force and my electric field are vectors. When I get to potential, I've got a scalar quantity, and all I have to deal with is the magnitude. Just like when we were dealing with my forces and my potential energy and my kinetic energy, I didn't necessarily have to worry about it. When I got to energy, I only dealt with the magnitude. I didn't have to deal with the fact that I had those vector sums. So the electric potential at V is just due to some point distance away that I'm away from my point charge. So I have to know what my actual distance is, but the work required to be there to infinity without acceleration is that QV. So I'm going to deal with my point charge, is going to look at that distance, and I'm going to actually look at my potential energy, and I'm going to end up as I'm going to take a charge from infinity into someplace else. I'll look at the work that's done, doing the same thing that I have out there, and do the algebraic sums. So I can actually look at it and do a little bit different. On Wednesday, we're going to be working some of these potential problems so that you can actually look at it. And I have, let's see, I haven't gone over here yet, but I will show you what I've put up here on Blackboard. And I have not put this, this presentation up yet. I don't know if you guys all know now what we're supposed to do with the presentations, and I kind of will show you what I have done. So let's kind of look at that so you know what's available to you. And things are going to start changing quite a bit with a variety of different aspects. So let me go here. So my courses, let me go over here first. So if I go in here and I go to downloads, here's the last, this is the last PowerPoint that I had up on the slides. And if I go over here, there's a picture, okay? There's a picture on the PowerPoint. And if I go over here and I right click on the picture, I say format picture. All of these slides now, if I go over here and I look at my picture and I look at it, all of the slides for each individual picture that you see on the slide should now have a written description for you. Okay? So if you use a reader, a lot of different people will use readers and have the computer actually read to you. If I use a reader, my reader is going to pick up the description, any description that's actually written for the individual picture. And now, given some new regulations that are going on, if you'll probably find a lot of times if you go to just on any website and you go to just show me the text to save data, if you want to save data, you don't want to have the image come across, this image text will pop up on your website. And so that's one of the things that's happening is we're actually putting these descriptions in. So I haven't had a chance to put the descriptions in the PowerPoint that I'm showing you right now. I should have it up by the end of the week with all the descriptions in there, because most of my PowerPoints already have descriptions, but I may or may not have them, and I just haven't gone in and checked all the way to show you that those descriptions are there. So it's just something to be aware of where those things are. The other thing is I've been trying to get a lot of my recordings closed captioned. And I've done several of them already, but I haven't done all of them. So periodically, all of a sudden, you may see a YouTube link that says YouTube with closed captions that I'll actually close caption. I don't know if you guys have been doing it or not, but I find myself looking at the closed captions on Facebook a lot. I find myself dealing with closed captions when I'm in the doctor's office, because I'll have the closed captions. It's easier for me to read along than trying to actually hear what somebody is actually saying, especially in a busy area. Watching football games, those kind of things, seeing that closed captioning. So there's a lot of things that are happening out there right now that you want to kind of be aware of. So under here, in our course assignments and materials, and we are now, I think we're now week 6 as we started up. Yep. We're now week 6. I've got on here some extra materials. This is one of those things that I've got that actually goes through. This is a worked problem, and anything in green, I've actually got a voiceover. So you can actually follow this particular solution for this doing the electric potential at a given point, finding two electric potential given two charges. So I'm going to try to find the electric potential at this spot, dealing with this point and this point, and then I talk you through why I've divided something, why I haven't divided something, and this is a special PDF, and it just, anything that's in green, there's voice material for. So that's there on Blackboard to help you out when you're starting to work the problem. Here's a YouTube on potential, and as you can see, I've got a quiz that opens up tomorrow at noon. And it's primarily on electric fields and forces. There may be a couple of potential problems, but I think I have this due. Let me look exactly. I think I have it due on Friday late is what I have it due at. Okay. I have it due Friday, or the 24th at midnight, which is Saturday at midnight, because we're on odd days this week. So it's due Saturday at midnight. And so you should have, we'll have worked several problems by then, but the force problems and the electric field problems are already on there. So there is a quiz that's out there. And I will post this set of slides once I get all the descriptions into the different pieces. But I wanted to kind of show you what was out there, what was being done. So now we can go back here. I was just making sure you didn't have a question. All right. So now we've gotten that idea of that potential. So when you went into lab, did you guys do the mapping of the electric field over here in Tonkawa last week? That's what you did. You actually measured potential. You got lines of equal potential. That's what you guys are going to do over in Enid this next week, is actually do those mapping. So when I have a conductor and my conductor is in equilibrium, okay, when like for example, I just have a piece of copper wire. It's not connected into a circuit. It's not connected into anything. I just have a piece of wire. Or I have the sphere on the Van der Graaf generator and I'm not necessarily charging it up or anything like that. If I have a conductor and it has a positive charge, all the net charges reside on the surface. This goes back to where we were talking about flux and Gauss's law on Friday, that we remember that we have all those excess charges are on the surface. The electric field inside the conductor is equal to 0. So if you guys did one of the electrode patterns, because you'll do several different patterns, you'll do a lot of different things, and if you have it properly set up, and the paper's actually working, that's the other fun part. Sometimes the paper doesn't actually work. But if the paper's actually working, and on your paper you had an electrode that looked like this, and I put my little positive charge over here, and I had a negative charge set up over here, if I tried to measure something inside of this box, I got a bunch of zeros. Because my electric field isn't inside the box. My electric field inside the box is equal to 0. So I wouldn't have an electric field out there. And if I did this, and if I got far enough away, so if we think of our box, okay, and we think of our box, and I've got a little box here. If I've got my box and my box is charged, and I've just gone further away, so I'm looking at the scale, this is going to act very much like any kind of spherical source of charge, and I'm going to get an electric field that's going to be going outward from my box. It's going to go out from that direction. Then, if I draw my lines of equal potential, because remember what we said about the lines of equal potential is that they're perpendicular, so if I go around here, I ultimately would get, it's a bad circle today, I get a circle around my box. And I'll get another circle around my box, which is just a different equal potential line. So I get my equal potential line, and I can actually measure this voltage. And that's what I did in the lab. Or that's what you actually did in lab over here in Tonkawa. That's what you guys are going to do over in lab over in Enid. Is you're actually going to measure those equal potential lines. But the electric field inside my box is equal to 0. What we're saying with the electric potential is I can go and take my meter and I can read it. And as I come in from infinity, now remember that my potential is equal to K, Q over R. Right? So it's K, Q over R. As R is from infinity, that's infinity. You know, that number gets to be really small, right? That number gets really small. And as I come in here, that this number, as I get this, if I go, so this number is really small, and if I do K is approaching 0, that number is getting really big. And so that's why I'm going to get a potential that's going to look like this. It's going to come in, and I'm going to get that kind of a graph. And it's going to go as 1 over R. It's going to be proportional to 1 over R, depending on my charge in there. So it comes back from, if I'm bringing something in from infinity, or if I'm bringing something up very close, and that radius is getting really small, I'm going to get that singularity. Going back to the computer. So I get my lovely electric field inside my conductor is equal to 0. All my excess charge is on the outside. So the potential is constant everywhere on the surface of the conductor. Doesn't matter where I'm at, it's the potential everywhere on the surface of the conductor. The potential everywhere on the inside of the conductor is equal to the value at its surface. So the electric field is 0, but my inside, my value is equal to the surface. We've already talked about the electron volt, because that's just another way of dealing with energies. And I can draw my equal potential surfaces. And that's what you did in the lab. You can draw that equal potential surface. Now, if I have that equal potential surface, and if I move around on that equal potential surface, I don't do any work. It's kind of like when I'm sitting up on the tabletop, and I'm out there and I'm looking at my change of potential energy, I'm not doing any work. I'm not changing that potential energy at all. If I'm walking around on the tabletop, I'm still that same height above the floor. So it's the same kind of thing, and the electric field at every point on the equal potential surface is perpendicular to where we are. So it's that same kind of thing. So we did it in the laboratory, we've done our equal potential surfaces, you guys are about to do it, and we can draw those field lines perpendicular. So this actually helps us visualize the electric field. It totally helps us visualize the electric field. And that kind of links back our electric field and our potential. And if I have a dipole, this is what it's going to look like. And you guys probably did this in lab over here. You guys will do it in lab over in Enid. And you've got those nice lines where my field lines are in orange. My light blue lines show me those equal potential lines. And hopefully you got to play with some of those interactive videos to play a little bit with these equal potential lines. And speaking of which, I'm going to go back out of here and go back to the computer. Okay. You're still at the computer. It's just doing weird things. Okay. If I go to WebAssign and I look at WebAssign, you'll notice I did add here we go. I did some interactive and supplement problems. They're going to be due on Friday. And if you go in here and you look at the problems, so I'm going to go in here and look at them. They're very interactive so that you can sit there and step by step. It's going to look a lot like what you guys did in lab or what you guys are about to do in lab. I'm going to actually look at my test charge. I'm going to look at where those pieces are going. I'm going to do the simulation. And then there's some questions about the simulation. And now I'm also going to look at combination of capacitors, because by Friday we're going to get to capacitors. So these are very much interactive problems, and hopefully they'll help make things make a lot more sense when you kind of play through those problems. So I've added those to that. And then the resistors, hopefully we'll get to resistors on Friday, or start getting the resistors on Friday. And this is charges in electric fields. Capacitors are due on the, I'm probably going to move that. Let me go ahead and move that. I'm going to switch that schedule. I don't want to do today, or do it on Friday. I'm going to switch it. Scheduled a week, this one. And we're going to have it due Monday. And that's definitely going to get scheduled later. Glad I looked at that. So that those are all kind of redistributed. So let's go back home. Back here. So now you've got the resistor pre-work is due on Friday. The supplement problems are due on Sunday. And then this stuff is still due. That stuff has already been done. That was due Friday. And now my capacitors are due next Monday. So that should be all kind of working through everything. And those should be all back to normal. Okay, so I've got my equal potential slides, or equal potential lines, and then we can look at those surfaces. So why do we use these? Well, I can use them for a variety of devices. One is an electrostatic precipitator. By putting those electric fields out there, I can capture small particles of dust. We use these at the refinery. A lot of you might have an electrostatic precipitator at your house, because a lot of air filters use electrostatic precipitation. It really helps to eliminate the mass of ashes and things that are going into the air, so it helps keep the air clean. I can use it for farm equipment. We can use it, a lot of our laser jet printers are done this way, inkjet printers, so that's how we're actually going to get it, and we can get those. So we use electrostatics in a variety of different ways. Now that gets us to capacitors. So my capacitor is a device that we use in an electric circuit. If you recall, you used to hear a capacitor charge up. We don't hear it so much anymore, but if I had a digital camera or if I had one of those little disposable cameras and you hit the button and you hear that high-pitched whistle that goes, it actually was loading up the capacitor. And that we could get the flash that hit when we release the charge in the capacitor. So a capacitor is a device that we use in electric circuits. It's going to store charge. Capacitor is going to store charge. And the capacitance is defined as the ratio of the charge on the plate to the magnitude of the potential difference between the plates. So think about that for a second. It's defined as the ratio of the magnitude of the charge on the connecting plates to the magnitude of the potential difference between the plates. It's going to be related to how far apart the plates are and how much charge that we put on the plates. So it will actually go there. So this is what mathematically it's saying that we're doing. Capacitance is equal to the charge divided by the potential difference. We're going to use lovely units called farads. Farad is a coulomb divided by the volt, and 1 farad is big. 1 farad is a big number. So we typically will be dealing with microfarads and picofarads. Micros 10 to the minus 6, picos are 10 to the minus, micros are 10 to the minus 6, picos are 10 to the minus 9. The potential is the difference across the circuit, and it's given due to the actual charge of the circuit. So let's kind of look at our device a little bit. Let's look at this device a little bit. I'm going to the document camera. Just thinking about it. Okay. So what we said, and we kind of showed this before, if I'm drawing my electric field and I have a plate, so we're gonna look at the plate side on. I've got a row of positive charges here, and I've got a row of negative charges. So I've got that. My capacitor is going to be worried about the distance between the two. And we know inside this right now, and when I deal with looking at my electric field becomes very uniform inside of my capacitor. If I did this in lab, or if you've already done it in lab, you actually saw that when I got to the edge, I started getting things that look like this. And that's known as edge effects. Okay? Those are known as edge effects. But I got a nice uniform electric field. If I look at this and I draw my equal potential lines, I get a line right through here. I get my equal potential lines. They're nice and perpendicular inside my set of my plates for my capacitor. So this is a capacitor. That's what we're going to be working with, and that's what we're going to be looking at having that actual device. Go back. And I can make capacitors very easily. I can make a capacitor using aluminum foil. I can make it anything. My plates have to be conducting plates, and then I have to have a gap. So this is how I get a parallel plate capacitor. I take two plates. Each plate has an area A. They're separated by a distance D. The plates are going to carry equal but opposite charges. And when connected to a battery, the charge is pulled from one plate and is transferred to the other plate. And the transfer stops when the potential across the plates is equal to the potential across the battery. So I'm going to be able to write and work problems looking at whatever my battery is connected to. I can have my plate fill that up, and I can actually get that potential across those plates. So if I have a 1.5 volt battery connected to 2 parallel plates, I get a 1.5 potential across my plates. So I can build that up. So the capacitance of the device depends on the geometric arrangement. So it's going to be based on how the device is set up, how far apart my plates are. So for a parallel plates capacitor that are separated by air, and we're going to find that different materials are going to impact my capacitor differently. Air, K is equal to 1, and that's called a dielectric constant, and it's referred to by the material that we have. So my dielectric constant for air is assumed to be 1. My capacitance across my plate is going to equal the permittivity of free space, that's my E, times the area divided by the distance. And if I don't have air between my plates, I have to worry about what the dielectric constant is for that material. So dielectrics can be rubber, can be cardboard, can be wax paper, it can be anything that doesn't create a short between my plates, okay? Because if I have a short between my plates, the charge is just going to go right through and I'm not going to be able to store charge. So I want to be able to have that. The capacitance is multiplied by a factor K when the dielectric completely fills the region between the plates. So I can fill it, and that's what happens when I buy a capacitor. My capacitors will have something with a dielectric constant in there in order to make sure my plates never touch each other. So it can be a lot of different resins, it can be a lot of different things that we can actually use, and that's where I'm going to have that dielectric constant. Your book has tables of dielectric constants, and we can do it. And I'll bring materials to build one on Wednesday so that we can actually see it. So I've got my parallel plate capacitor. One side's going to be charged with a positive, one side's going to be charged with a negative. The electric field is uniform. And we say near the center, doesn't have to be that near the center. It's going to be gets pretty uniform all the way. And it's non-uniform near the edges, so I do get edge effects. And the field may be taken as constant throughout the region between the plates. So that's what we end up doing. That's how I build a uniform electric field. So if I want to do an experiment, which is what I did as a graduate student, what we were looking at was measuring van der Waals forces, and I would put charged particles between 2 plates and actually look at how those things interacted. So that's how I created my electric field that I was utilizing. So I could get that nice uniform electric field. So how do we use these things? Flash on my attachment for my camera. Very common example. There's another way we use it. We use it a lot. I can use it associated with my keys on my keyboard. I have a capacitor in there. I can touch it. I can use the basic on the keys. I have a movable plate. When I hit it down, it's recognized as a change in capacitance, and that's how the computer tells which key I've hit, because I have that actual change in my capacitors. Now, start talking about electric circuits, because we're going to end up with 3 devices that we have to deal with, and we're going to use an electric circuit, and it's a collection. A circuit is a collection of objects that usually contain a source of electrical energy, such as a battery, and converts that energy to other forms. And then we can use a circuit diagram to describe the circuit. So let's kind of start talking about this, because that's where we're headed. All right. So we're going to use a variety of symbols to represent our devices in the electric field. So I'll do this one. This one's a nice bright one. So my battery is going to be represented like this. This is the positive side of the battery, that's the negative side of the battery. And when we draw it in a circuit, I'm going to act like I'm drawing it with a little bit of a wire. So this is a battery. My capacitor looks very much like a battery, because we actually show that those change in potential is the same. these lines are usually drawn to be the same length, and that's my capacitor. Can't spell today. That's my capacitor. Then we'll have something that we're going to get to really quick. It looks like this. This is my resistor. So this is going to be represented by a C. This is going to be represented by an R. Then ultimately we'll get to another device, and it'll look like a little curlicue here. And this is called this is called an inductor, and it's represented by an L, and it uses something that we call impedance. Okay, so capacitors, resistors, and inductors. This gives me something called impedance, and we won't get to this until after we do magnetic fields. B represents a magnetic field. Whereas E is my electric field. So I've got my magnetic fields are B, and this one is going to depend on my magnetic field, so we won't get to it for a while. But we're going to work with capacitors and resistors for a little bit. So capacitors and resistors. And resistors are things that are going to hinder the current in my circuit. So if I'm drawing a circuit right now, this is my battery. So this would be a circuit that just contains a capacitor. Usually what we'll tell you is this is like a 1.5 volt battery. If I want to draw a switch in my battery or my circuit, that's how my circuit draws a switch. So this is my circuit when it's open. There's my switch when it's closed. So I'm starting to work with my circuits in order to get my circuits in there to work different things. So I can use a circuit diagram to get me to start talking about where things are. So I'm going to put capacitors in my circuits, I can put resistors in my circuits, and the circuit diagram can be shown to show the electrical circuit. So my mouse uses a capacitor, okay? My mouse uses a capacitor, and in fact, there it is. There's where my mouse is, there's my capacitor and my mouse. These are resistors, and these being grounds, and here are my switches. Those are my different switches. And there's my capacitor. So this is a simple electrical circuit diagram for an optical mouse that we use on a computer. So I can actually draw those. So I'm going to stop there because I want to work some potential problems for you, and I don't want to start doing capacitors and parallels and other stuff until after we've worked a couple of problems. And then we'll see you Wednesday, and we'll build a capacitor too.